Well, my name is Christophe Gengnagel. I'm a professor for structural design and engineering at the University of the Arts in Berlin. And I think 8 years ago we had this idea to find or to develop a space for discussion and exchange of ideas and visions. This was the original concept of the Design Modelling Symposium, to be a place for architects, engineers, artists, and product designers, so a lot of different approaches working together in the world of computational design or computational fabrication. Okay, in this afternoon, or it will be a long afternoon, we discuss, or we will have a lot of talks about material and as well about design environments, design tools for architecture, but also for maybe smaller scales as well. It's about designing probably a new world, physical world with new possibilities to simulating behavior, material behavior in very early design stages. It's one, I think, very important idea of a lot of research that we are working all together, and the other ideas to work in a different way in fabrication process, but also different way with materials. So we are very proud to welcome as the first speaker of this afternoon, Achim Menges. Achim Menges is well known. He's working in the area since, I would say, a lot of years. Since 2008, he's professor in Stuttgart at the Department for Computational Design and Manufacturing. He's coming from the AA, where he also did a lot of, I would say, fundamental work and implementing computational design and architectural education, working as a unit master for, I think, almost 6 years or longer. He moved to Offenbach, was working as a professor there as well in Germany, and now he's, on the one hand, still working in a very exciting research group. It's Sonderforschungsbereich. It's, they're doing a lot of work with, in the field of bionics and trying to combine this concepts and knowledge together with architectural design. At the same time, he's working as a professor at the Harvard School of Design as guest lecturer.
I will take a couple of minutes to introduce the overall kind of ambition of our work and also the mindset which we try to embrace. And I think that's very closely related to some of the things we've seen already this morning that got me really excited. So I think in our research, we really try to embrace a particular contemporary condition of architecture, and this is that we strongly perceive that the physical and the virtual are beginning to merge. And I think that was really evident in almost all the presentations this morning. So while one can argue that the separation between the processes of design and making, which really have dominated architecture design thinking as being separate, and this separation being largely intact, one can already sense that a new understanding of the material in architecture is beginning to arise, where the material can actually be rediscovered through the computational. So in other words, as Sanford Quincy puts it, computation enables us to engage aspects of the material world whose logic had previously remained ungraspable because they were lodged at too great a remove from the modalities of the designer's sense and intuition. I think that is quite a fundamental shift, and I think it also hints at the computer having a more fundamental role than being just another tool in a kind of chain of new tools that have arrived and transformed the discipline. Of course, it's also important to say that a material-oriented approach to design, and in particular architectural design, is not without precedent, particularly in the 20th century. For example, one of my favorite examples is Joseph Alber's material studies that he conducted at the Fokus at the Bauhaus in Dessau, which in my eyes establish a very interesting precedent for the possible enrichment of design processes through what he actually called material experimentation. And it's quite interesting to note that Albers rejected established processes of materialization that are based on craft knowledge because he claimed that they stifle invention. And instead, he identified the material behavior itself as a creative domain for developing new modes of construction and innovation. So his material studies, of which you can see one here, the famous paper studies, it's a bit later than the Bauhaus, that's already at the Black Mountain College. It's important to understand that they were not conceived as scalar models or representations of preconceived ideas, but really as the temporary unfolding of material behavior in space and time, which become the origin point for an architectural idea. At the other end of the spectrum, another interesting example for our work and precedent are Frei Otto's extensive series of experiments that he conducted at his institute at the University of Stuttgart. Through what he called form-finding methods, Otto investigated, as you probably all know, a vast number of different material systems in order to study their capacity to physically compute form. So I like to think of our work as trying to embrace both Albers' experimental approach of employing material as a driving force in an open-ended creative process and Otto's scientific rigor in conducting design research that investigates the formation of form and structure in both architecture as well as nature. So similar to his work, but in today's context of computation, design, simulation, and fabrication, we also try to explore the repositioning of the role of technology in architecture, shifting from a mechanically to a biologically informed design paradigm based on a synthesis of form, material, structure, and performance that finds its conceptual roots in the process of becoming in nature, which we usually call morphogenesis. Morphogenesis is a process, and that's the interesting part for our work, in which formation and materialization are inherently and absolutely inseparably related. And the interesting aspect here is that this enables natural systems to achieve unmatched performance through a high level of morphological differentiation. Because, as Julian Vincent aptly stated in one of my favorite quotes, in biology, material is expensive, but shape is cheap. And then he goes on, interestingly, as of today, the opposite was true in the case of technology. Now, arguably, with design computation and robotic fabrication, this is about to change and thus enables us to tap into the vast reservoir of morphological, constructional, and procedural principles that we can find in nature. So in this way, the study of biology within interdisciplinary teams enables us to question deeply entrenched disciplinary conventions that really determine our design thinking very often and allows us to rethink, so to say, the very flesh and bones of architecture. So in summary, I might say that our research aims to exploring the notion of material-informed design and its manifold and deep interrelations with technology, biology, and culture. And as we try to pursue that, not only as a technical, but also as an intellectual venture, we try to sort of also contribute to the emergence of a novel computational material culture in architecture. So we have done that for a whole number of materials. So I think this is not a material-specific approach. We've worked a lot with timber, with new timber contactions, such as these robotic sewing for these segmented shells. We've managed to actually transform that into first permanent demonstrator buildings, and we're very happy to see that now actually migrate into fully fledged architectural projects like the one that we're working on right now in Germany. But today I will focus on one specific family of materials because they are particularly challenging to the way we think about materials in architecture, and that is fiber-reinforced plastics or composites that are made from them. So this is an interesting family of materials from many points of view, and I will try to hint at some of them. But I will begin with something that is quite surprising, which is that, namely, most load-bearing structures that we can find in nature are actually fibrous systems. Even more astounding is that given the incredible diversity of natural systems, that actually nature only employs 4 fundamental fiber materials for doing this. That is cellulose in plants, as you can see here, collagen in animals like us, chitin in crustaceans and insects, and then sort of as an oddity, the silks and spider webs and so on. And what is also interesting is that the actual performance is most of the time not achieved, maybe with the exception of silk, by the actual material properties, but by the way these materials are arranged and organized in space. And that is obviously very interesting also from an architectural point of view. What is also astounding is that those natural fiber materials fundamentally, like the collagen fibers that you see on the right, work on a fundamental level very similar to technical fibers that we know, such as carbon fiber or glass fiber. Yet, we also probably have made the experience that those materials are very counterintuitive to the way we usually think about construction materials. So here you have a material that starts off as something that is incredibly soft and flexible. That's a spool of carbon fiber. Only through the kind of impregnation and curing with the resin, it becomes as strong and stiff as steel. It's a material that's incredibly lightweight. So all of a sudden you have 1 kilometer of building or construction material that weighs less than 1 kilogram. So it really requires us to rethink some of the fundamental logics of how we think about design, how we think about making and construction. The first project along which I want to sort of give a hint at those interesting consequences or ramifications is a project that we completed last year for the Victoria and Albert Museum as the kind of centerpiece of the engineering season, which is sort of this pavilion canopy in the central courtyard of the V&A. So this is not only a showcase for a different way of thinking about the integration of design and engineering, of how the physical and the computational meet, but it was also an architectural competition where there was a straightforward task to basically cover the courtyard with a canopy that extends the possible use of the courtyard being located in England, exposed to rain fairly frequently, with a kind of, by creating a semi-interior urban green space. So for our proposal, we were able to sort of tap into multiple years of research that we had done on investigating the transfer of biological principles of or sort of the constructional principles of biological composites to architecture. And one particularly interesting sort of biological fiber structure is shown here, and this is the forewing of the beetle called, when there are two, elytra, which gives the pavilion its name, which is this hardened shell that you can see here in the circle, which actually protects the flying wing, which is this fragile, transparent structure here on the right, from being damaged or injured while the beetle crawls on the ground and sort of hides in recesses in rocks, etc. So what is interesting is that for terrestrial beetles, this shell is a solid slab of material, as you can see on the upper left, where you have a cross-section through the shell. But for flying beetles, it's this incredibly intricate, incredibly lightweight structure that is made from a natural composite of chitin fibers in a protein matrix. So we investigated that structure with the use of this handy tool, which is a particle accelerator that we had access to at colleagues at KIT in Karlsruhe. So we managed to actually use that to do microcomputer tomography of that shell structure, which you can see here, where you can nicely see how computation also extends our sort of realm as designers, not only sort of upscale, but also downscale to something that has the resolution of 3 to 6 microns. And when we zoom in to these models, we begin to get an understanding of what sort of the secret behind the high performance of the beetle shell really is. And for that, we need to zoom into a little bit further, and then we see that the way that nature constructs that fibrous shell is very counterintuitive to us in architecture or structural engineering, which is that it's a double-layered shell, but it's made from one continuous material where all the fibers of the upper surface continuously actually go down into the lower surface. So there's not a kind of upper and lower surface that is connected by a couple of sticks, but it's all one material structure. So this is one of the fundamental principles that we try to abstract and turn into a building system, which you see here on a principle level, which is made from a glass fiber body that generates a form, and then onto the glass fiber body we're able to lay carbon fibers exactly where they need it, similar to the beetle, in a kind of response to the local forces that can be observed. So what is interesting is also that when we usually think about those synthetic composite materials, we consider them being amorphic. That means that they are inherently shapeless. And that's why we usually invest a lot of time, effort, money, and resources into building the molds that allow us to shape them. As you can see here, that's a wind turbine blade being manufactured at Siemens. So it is surely a building scale element, but you get an understanding that you have to do a couple of those blades before really the investment is returned. So obviously, this is something that is economically difficult, but we also think that is intellectually not very satisfying. So over the last couple of years, we have developed moldless fabrication processes for fiber composite materials, where we try to reduce the formwork to a very simple scaffold, as you can see here, where we actually use the capacity of the fiber to form a structure itself by deforming continuously the previously laid fibers in the build-up process. So this is maybe something that's clearer in the video. So here you can see that. So we don't cut the fibers, we don't chop them, we don't use stock materials like fiber mats. We just use the roving, which is bundles of fibers, 50,000 fibers, all being in one direction. And they're laid in a wet state, as you could just see. So they run through a resin bath, and then they're impregnated with the resin, and in that state, they're applied when they're still flexible and wet onto the framework. And then initially, this hyperparabolic body of glass fiber is built up, and then the carbon fiber is laid onto that embedded mold, so to say, in the way that is actually needed for each single component. So it's a very different way of working with carbon fiber, removes one of the biggest problems when it comes to recycling, namely that the fibers are usually chopped. Here it's actually made from one string of material, and it results in incredibly lightweight components that are ultimately equipped with a polycarbonate skin to offer proper weather protection. It's also interesting to note that with exactly the same tool, we can build these column-like structures as well. So with one tool that can be collapsed and is obviously removed after the fiber is cured, that's important to say, we can build an infinite number of differentiated, finely calibrated to the actual force requirements set of components. So this is done by having a direct feedback between the structural analysis, which happens on the one hand on a shell level, on the other on the actual level of the fibers. One of the competencies of the ITK Institute at Stuttgart, who we collaborate with on all these projects, so that we And that is then fed back into the manufacturing process and becomes a trace in the architecture articulation, as you can nicely see here, where the upper corners are obviously more strongly reinforced than the lower ones. And there's a lot of subtle differentiation which accumulates throughout the roof and actually really creates an interesting perception of that canopies. Another interesting aspect is obviously that here you have an element that covers 5 square meters of roof, but only weighs around 50 kilograms. So the specific weight is less than 9 kilograms per square meter for sort of on average. And that obviously begins to also trigger other kinds of ideas, because it challenges our conception that construction materials need to be heavy, bulky, lifted by grains, an incredibly involving procedure. Even more so if you consider that the production unit that you need to produce these elements is tiny compared to most other manufacturing facilities that we usually engage with in the construction industry. So you need a kind of 6 or 7 square meter tent. The robot sits in there. You show up with a bucket of resin and a small spool of carbon fibers that weighs, as I said, less than a couple of kilograms, and you can produce all these elements in that unit. And that obviously means that also our conception of a building site becomes challenged. We can begin to think about local production, and local production means also that you don't have to think of a strong delineation between the construction phase and the phase of using the building, but you can begin to think of that as more as a continuum where your structure, enabled by the local production, lightweightness of the materials, becomes an sort of ongoing design and construction process that does not have a preconceived final state. So in order to test that and use the garden of the museum almost as a laboratory for that experiment, we really wanted to have the pavilion becoming a kind of dynamic space and evolving structure that has the ability to sense critical input, in our case, environmental, structural, and the way that people engage with the pavilion space, and from that basically generate new elements that allow the structure to actually continue growing and adapting to what's going on in the courtyard. So in order to do that, here you see one of the initial states. We prefabricated quite a significant number of these elements in Stuttgart, but then we began to monitor how people are actually beginning to occupy that space, how they basically distribute and inhabit the semi-interior environment given the particular spatial and environmental conditions. For that, we equipped the entire structure with sensors that allow us to do, on the one hand, sensing the kind of environmental criteria. This was done in collaboration with our colleagues from Transolar, who actually also managed to, in real time, compute the UTCI. This was all live on the website, so you could actually check that continuously. And at the same time, we monitored on the right how people actually engage with the space entirely anonymously, so that you begin to perceive patterns of space use. The idea was here not to actually have a very linear causal relationship by saying, lots of people sit in the shade, let's put a little bit of more of a roof here, but it was really about thinking of the pavilion more as a kind of learning machine that actually probes the pavilion. Seems to be stuck. Let's see. So the pavilion was more conceived as a kind of learning machine that begins to probe certain situations and then gather the data, how people respond to that, because obviously you're not naive enough to think that everyone just navigates through the space because there's some shade, but to get a kind of understanding of the subtle interrelations between the articulation of the envelope, the sort of microclimatic differentiation that is achieved, and how that can actually influence our itineraries through the courtyard. Now, one interesting aspect is that, of course, we also needed to make the proof engineer that the VNA appointed for the project happy, and you can imagine it's a bit of a challenge if you have not a finite end state that you can actually plan for. And I think this is the paradigm that we have already heard about this morning, that we now have the possibilities, especially with the fiber structures, to embed sensors in the canopy itself. In this case, the interesting part is that the glass fiber can obviously also sense strain and thus forces. So with our colleagues from ITKE, we were able to have these fiber optic sensing devices in the canopy, and by that we can sort of monitor the actual sort of forces that the canopy experiences, and from that actually plan the next step of reconfiguration and growth. And I think that is definitely a very interesting enabling technology for also rethinking the permanence that we usually assign to these structures. So what is important to note is that the structure reconfigured through a number of specific events while it was in the courtyard of the VNA. And I think the other aspect is that it really, I think, for us was the first indication of what a fibrous tectonic in architecture could be, because I need to remind you that there's the only load-bearing material in that roof that has about 225 square meters are carbon and glass fiber. There's no steel, no nothing. It's just fibers. And that, in return, means that it's an incredibly lightweight structure. So the entire roof weighs about 2 tons, which is the same as 2 square meters of the brick wall of the VNA. So it is really a different dimension of lightweightness. What is also interesting is that obviously the glass and carbon fibers have a very different sort of way of showcasing how the structure works, that on the one hand is very counterintuitive, but on the other hand, they follow a certain logic and allows you to understand, let's say, the tectonic articulation, even without necessarily knowing that sort of construction system on and of itself. A last interesting aspect is that the glass fibers also have the ability to pick up the light, which means that at nighttime, where the structure was illuminated from within the columns, it forms this kind of hovering cloud above the courtyard, which was incredibly popular with all the nighttime events that go on there. We're also very happy that with that system that we developed for the VNA, we now have made also with this the leap to actually sort of privately commissioned structures. We're currently building a larger canopy in a very prominent location in New York, and we hope to complete that by the end of next year. But obviously, that idea of reducing the formwork and by that trying to tease out the self-expression of the fibers as some kind of architectural exploration is something that can go quite a step further, and that's what we tried with this research pavilion, where we looked into the minimization of the formwork to an inflatable onto which we then actually lay the fibers, so that ultimately the kind of inflatable becomes stabilized and becomes a compression shell. So there are good reasons, we were told, why nobody has embarked on using pneumatic formworks for carbon fibers, because you have a material that has hardly any elasticity, and then you have a formwork that most likely is going to deform in the construction process. So these two things don't go very well together. But then it's interesting to see that in nature, there are examples where this contradiction has been resolved. And this is one of the cases, which is the water spider. So what we see here is an underwater photography that our students took in the basement of a spider that they nicely kept there. And what is interesting about the water spider is that it's an animal that needs air to breathe, oxygen to live, but its habitat is underwater. So what it does is it builds this kind of loose web that you can see, and then it actually transports smaller air bubbles from above the water surface down into the water, which are caught by the web, and then actually builds up this diving bell, as you can see here. And once that has a sufficient size, it enters the water bubble and reinforces it from the inside to form a stable structure which becomes the habitat for the spider. So somehow the spider manages to do what is the technical challenge, namely adapting its kind of fiber path and the fiber layout continuously in the process of building up the structure on a constantly deforming mold. So we were embarking on doing a very similar thing sort of from a technological perspective, where we take a standard construction material, ETFE foil, as the one that you can see here in the courtyard, inflate that. As you can also nicely see in the courtyard, you need constant inflation if you want to have it as a pneumatic structure, so we didn't want to have that, but rather we inflate it. Then we have the robot applying the carbon fibers on the inside, and once a suitable sort of stage is reached to actually take all the forces acting on the structure in compression, the robot stops, the air pressure is released, and it works as a compression shell. So at the beginning, the membrane carries the fibers. At the end, the fibers support the membrane as the kind of embedded building envelope. Obviously, that again requires to know about two distinct states, the fabrication state, the pneumatic state, where the whole thing is basically in tension, and then the final state, where it is exposed to all kinds of forces, because we engineer, or we need to do a full planning application for these structures, even though they're experimental. So we do the whole kind of approval process, which obviously entails wind, snow, all these things. That project was actually on site for a year. So because this is relatively complex, we mapped these two distinct states into one computational environment, and then we developed an agent system which, similar to the spider, actually navigates through that design environment and leaves a trace of fibers behind, following basically the requirements for both structure states. Now, what is interesting about that agent model is that this is another instance where it becomes very clear that design and making become sort of fused through the convergence, or can become fused through the convergence of the physical and the digital. Because what we needed to do for this project is that we developed what we like to call a cyber-physical fiber placement system, which means that the robot actually gathers information from the environment by having sensors that allow the robot to basically sense the pressure with which the fibers are applied, the pressure in the membrane, and also scans ahead to see where there are already fibers, and then makes a decision about its final path of laying the carbon fibers on the surface. So towards the end of the fabrication process, you can see it looks like this. There is a certain order because it tries to basically approximate the main load paths. But then there's also a kind of emerging random pattern because it needs to cover enough area so that there's no water sacking possible if you have more than about 10 by 10 centimeters of ETFE spanning freely in space. And then once that suitable compression state is reached, you just cut out the openings and you have a compression shell that just stands by itself. So on the inside, I think the initial softness of the roving bundles remains quite nicely tangible in the fibrous texture, which strongly contrasts with the actually hardened state. And I think that evokes at the same time quite a strong sense of transparency and even airiness, as well as a kind of tangible tautness of this extremely lightweight structure. On the other hand, on the outside, during daylight, you basically just perceive the very glossy ETFE surface, which then is transformed substantially at nighttime when it's illuminated from the inside, where the whole fibrous texture becomes visible. What is interesting is that, to me, is that here we also collaborated with the Institute for Aircraft Design and Engineering at the University of Stuttgart, mainly on developing the pre-impregnated fibers. So the carbon fibers are actually frozen and pre-impregnated with the resin. But what is interesting is that when we started the project, they considered that as being something that only uninformed people, to say diplomatically, would do. But in the end, we achieve to build this entire structure with a diameter of 9 meters, 5 meter tall approximately, with a self-weight of 260 kilograms, which even in their value system is a pretty remarkable achievement. So you can see that if you sort of take the unorthodox path of the designer, sometimes it even allows you to innovate in the quantitative world of the aerospace engineer. Because this is all better captured in a video, I will show you that also to cheer you up and wake you up a little bit after lunch. One thing that you become acutely aware when you look at the of this mini building is that one of the key constraints is the reach of the robot. So in the next set of experiments, we are trying to obviously challenge that as well by looking into ways of how we can actually extend the reach of the machines by a smart combination of their capabilities. So this is a subsequent project that we completed this year, where we looked at how we can combine the precision, the strength of the industrial robot, which we need to monitor and precisely apply the carbon fiber in a pre-stressed state, but then how we can sort of have that complemented by a long-range machine that does not need to be particularly precise, but has a far wider reach, which in this case was a flying drone. So that means that you need to make machines basically interact that are not meant to interact whatsoever, which obviously gives you also an understanding of the expanded idea of what design in such a case entails. I think this is one of the key pedagogical lessons for all of our students, that being a designer allows you to actually interact and extend and literally design all of these processes into action, and by that enable new possibilities, even for the discipline of architecture, of which you can see one result here. So you can see the two robots on both ends, and then you can see the drone basically flying the fiber from one end to the other, which you can see here in this video, which is, in this case, a really kind of autonomous process, because the drone navigates basically by itself, which was difficult because it's kind of indoors, so it needs to have markers everywhere. And then it hands over the bobbin to the robot. The robot finds the drone, and then it applies the fibers onto this kind of demonstrated structure, which again I think is showing how, let's say, fibrous materials really begin to allow us to actually make use of machinery that usually would not be considered to be very well suitable for construction processes. That's really only afforded and makes sense if you have a building material that, as I mentioned before, weighs 1 kilogram per kilometer. So the result in this case was this cantilevering structure, which we considered in this case more as a kind of demonstrator of one building element that you could produce, but that could then be, if it's arranged, form a much larger structure, basically cantilevers around 12 or 30 meters and weighs roughly a ton, but is designed for a weight of 5 grown-up men at the tip. But in the end, I think it also shows that once we begin to engage with these materials, we may have to think of the relationship between the machine and the fabrication process and the materials in a different way. And rather than thinking of scaling up the structures and scaling up the machinery at the same time, we may want to actually scale down the machines, make them more agile, and have loads of them. So this is something that we also experimented with, starting with this interesting master thesis by Marina Jablonina, who actually really engaged with the fact that in biology, the producing agent is actually tiny compared to the structures that it builds, especially if they're fibrous. So she developed these wall climbing robots that can collaborate to build larger structures by carrying a bobbin of fiber and by an interesting way of actually making them interact. So here you can see that basically you have two of these wall climbers, and they pass the bobbin and from one to the other, and by that the kind of larger structure emerges. That opens up all kinds of possibilities. If you want to see the video all to the end, you can actually check it. It's on our website. And Maria has worked hard to extend that. And she has now also a kind of fiber shuttle robot. That does mean that you can not only work in 90-degree corners, but you can actually have the fibers shuttling from one sort of surface to the other, and has done an installation with that in Milan, and has just finished one with multiple of those working in collaboration at the Ars Electronica in Lienz. I have to come to an end, I guess. Thank you very much for your attention. Thank you.
Thank you very much. I'm even limited with time. I would like to allow one or two questions. Questions for Achim Menges.
Achim, quite a while back, we won a project with Hadid in Pau, and the hope was that we would build a roof which was about 40 meters in one direction and 60 in the other, with carbon fiber. At the time, the thing that killed the project were insurers. How do you handle insurers?
It's a good question, and there are two answers to that. The first is that these are the things that you don't see in a glossy presentation, but the project at the V&A came with a 500-page contract that made sure that all the kind of invaluable British and actually worldwide heritage that is in the V&A is safe, although there's this thing in the courtyard which is not accessible by a fire engine, for example, and needed to be carried all the way through the door, sort of through the hallways of the museum with the exhibits. So that is basically about having the ability to make the client confident that it's not going to fly around, which I cannot take a lot of credit for, but the remarkable engineers that we work with at in this case, Jan Knippers, made sure, and they appointed an external proof engineer to check everything. That's the one part. The other, and I think it's actually pretty remarkable that construction innovation needs a cultural institution to have made this possible. That's something that should go, that's something that I try to address when I speak to the science foundations quite frequently. That's one aspect, interesting aspect, but I think in the end, what we're also trying in parallel to these projects is now actually a whole number of research projects where we look into flame resistance, UV protection, and all these things. Since that Zaha Hadid project, I think it also needs to be said that carbon fiber has entered mainstream mass production in other fields, and a BMW customer is also not very happy if his carbon fiber roof on a car that costs 150,000 euros is going to fade into some nasty color. So I think there are some issues that have been resolved by the industry, by other industries, but we still need to actually catch up with that, and fire and UV resistance is a big one, but I think there are interesting possibilities that we're beginning to, or that we have begun to investigate at the same time as we look at these design experiments. Yeah.
Another question?
No.
Okay, so that's a question.
Thank you. I have a question about the path that the spider takes to put the fibers. Do you have an idea on how it chooses the path and whether it is optimal? And maybe that you could use it to make it with a robot that would choose its own path without any calculation a priori calculations, if you understand what I mean.
Yeah, well, what we did, actually not only that project, but all of these projects come with a lot of other biological investigations that are not turned into structures, but what we did quite extensively is actually monitor the way that the spider builds the web, and try to sort of understand what the biologists call the behavioral stereotypes, which are basically the algorithms that the spider actually executes over and over again, but not entirely, because it responds to environmental stimuli. And that's the kind of sensing that takes place. So the spider is always produces and senses at the same time. And that's what we're also doing or beginning to do in these kind of systems. But of course, you need to have an idea of how it's going to work as a kind of overall structure. So you cannot resolve everything through local sensing, especially not in the fabrication process. I think that's a misconception that is predominant in a lot of places, but obviously you can amend that model and you can keep having it evolving, but you need to have some idea of where is it going to go, and then how you amend that on the fly, so to say, with the input that you get from the environment. But that's something that you need. And that's also what the spiders have embedded, so to say. But it's interesting that, for example, in arachnology, which is kind of the biologists that look into spiders, they have developed the most sophisticated ways of monitoring the layup of webs and the kind of patterns and the whole behavioral stereotypes that actually allow that to take place. So a lot to learn for architects.
I think we have to
Okay.
ask further questions to the coffee break, probably. Achim will be there.
Okay.
If you have further questions. Thank
you.
you very much again.